Okay, welcome back. We're talking about the pre-processed coefficients technique. Now, there's not really a good example in the book, but let me just talk about it in general. So, I have a coefficient of 6 and I have x. So, my value of x is 2. So, I can go ahead and take the 6 times the 2 in advance. I don't have to wait until I get there. So, I can do a lot of the multiplication up front. Okay. Now, once again, what that's going to do is going to reduce the amount of multiplication, but increase the amount of addition that has to take place. So, is trading multiplication for addition a good deal? Yes, it is. So, standard technique has lots of multiplication. Horner basically cuts the amount of multiplication in half, and preprocess cuts it again by a huge chunk, but at the expense of a little bit more addition. Now, one of the other things that preprocessed coefficients can do for you is, let's say, not all polynomial equations have every single exponent. I mean, it could be something to the fourth plus something to the third and not have something to the second at all. The second, right, just skip one. Well, that coefficient in the array will be a 0. And so when you're doing preprocessed coefficient, it basically says, stop, we don't need to deal with this one, just move on. Poof. There's no need calculating anything. If the coefficient is 0, well then I don't care what the exponent is, move on. So it has some other types of things that can help out. Okay, so next we're talking about matrix multiplication on page 137. So I found a really cool website I kind of like. It's called Math is Fun, and it talks about how you have a two-dimensional array, a matrix, and if you're multiplying it times one number, well, that's pretty easy. It's just 2 times whatever that is, and 2 times 0, 2 times 1, 2 times negative 9. It's no big deal. But if you have one of these times, by multiplying one of those by one of those, it's called a dot product. That's the cool name for it. And basically, so just looking at one row and one column, so here's a one row and one column, it's that one times that one, plus that one times that one, plus that one times that one, equals 58. And ka-dunk, you put that in that spot. And so that's how this dot product thing works. You take, each element in the row and each element in the column, and you multiply them together and plunk them in the right spot. Kind of, sort of simple. Okay, so I kind of like this math website because it's pretty cool. But the way they're talking about it on page 138 is, okay, I'm sorry. Yeah, preprocessed coefficient. This was the one using, 7, I think it was. I don't remember what it is. Here's the general version of that, where you can calculate what the efficiency would be for any polynomial. Okay, so here we go. So here's their example of showing that same thing. So this would be a times 1 plus a, b times 2 plus c times 3, and then it scoots over, okay? Cool. Now, one of the things you probably need to learn right up front is what is the size of the resulting. See, this is a 2 by 3, right? And this is a 3 by 2 matrix. So what is the size of the result? Well, the size of the result is always going to be the first number and the last number. So if it was 2 by 3 multiplied by a 4 by 5, it'd be 2 by 5. It's the beginning and the end. The rows and columns. Rows on this side, columns on that side. Okay? One more time. If it was 18 by 4 and 16 by 9, it's 8 times 9. Okay? Good. All right. So that's a good test question. Okay. So you guys remember the cumulative property and the commutative property, associative property? Maybe? Okay, let me bring up Math is Fun one more time. So, distributed property. Distributed property means I can do something like this. I can say, 2 times x plus y is the same thing as 2 times each one of those guys. Cool. Associative property basically means I can take this and split it apart. And then commutative property means I don't have to worry about the order. That 2 times 3 is the same as 3 times 2. Okay? Commutative property. Now, having said all that, now that you know what those terms mean, does commutative property apply to matrix multiplication? Well, I just told you how to figure out what the the resulting size is. So if a 2 by 3 multiplied by 4 by 5 is 2 and 5, and I did this to them, so now it's 4 by 5 by 2 by 3? No, it's not. So the commutative property here does not apply when multiplying math. But we do need some of those other things. We do need, associative property. Man, we need that thing big time. Particularly when we're refactoring. Okay. So hopefully that was a trip down memory lane from your early math days. Hopefully. All right. So if we were to do this, the trivial algorithm to do this is basically to do it like you would do by hand, right? I start with the two matrices, R and G. I'm sorry, G and H, whatever. And so I go through and I pick the first one, and then I go through and multiply, that one times that one must multiply. So this is how you would do it by hand. And there's an awful lot of multiplication going on and an awful lot of stuff. But this could be improved upon big time. By the way, sometimes this is called the standard process. Sometimes it's called the naive process. It's just a term that basically means this is the more obvious way to do it. However, there's a heck of a lot more you can do. So there's another technique called Winograd, and on page 138. And so they talk about how you can go in and pre-process some things and turn them into vectors. So what that basically means is, I thought I had a graphic on that. Doggone it. Okay, I don't. Basically what that means is I can do fewer multiplications and add some more additions to it. So it takes two pieces to make this thing work. One is a pre-processing phase. Well, I pre-process this and I go through and I calculate, some factors, a column factor and a row factor. Okay? And so after I've done this pre-processing allows me to kind of speed things up because I can do fewer amount of multiplications. And then after you do that, you do the calculating phase. And this is what the calculating phase would do. It takes the row factors and the column factors and and then it puts all the things back together. It basically does, and if it works really well, works really well when you have the same number of columns and rows. Makes it a little easier to deal with. But this is a technique called Winograd. And it's actually pretty good because it reduces the amount of multiplications. So the big O notation on these guys are all about the same in reality. The average big O kind of a thing. But one is going to be significantly faster than the other. Although this one does have some housekeeping that has to happen. So maybe if you had a small array, you probably use the standard technique and use Winograd for something that's a little bit better. And then there's another one called Strassen's method, page 140. And this works only if the matrices are square. In other words, they have to be the exact same size and shape. You can't have that. And so what some people do, because they want to use Strassen, is they'll add a row of zeros here and a row of zeros here to make them come out square. Okay? That's an awful lot of weird stuff, but I've seen people do it. And then you can use some divide and conquer kind of things. I mean, if you had a 4 by 4, you could treat it as 2 by 2s. Okay? That kind of stuff. And it has this really strange set of calculations that it has to go through, where it goes through and the first time through calculates a bunch of temporary variables. I mean, a whole series of temporary variables. And then it goes through and does the results. Now, I'm not going to go through all of that because it turns out that nobody really uses the Strassen method at all. Not because it's not good. It's just that it's too clumsy. It's kind of sort of like the radix sort we talked about in a previous chapter, where it's actually pretty doggone cool, but difficult to implement. Same thing here. There's too much housekeeping that has to happen, and particularly if you're going to do it recursive, the amount of housekeeping just explodes on what you have to keep track of. And so even though it's interesting, it's not really practically used. Most people use Winograd. Okay? That's the typical thing that people use. And you can kind of sort of see why. This is the amount of multiplications and additions that go on. So into the third plus divided by 2 and this one can actually beat it theoretically, but in theory it rarely does. It tends to chew up more CPU cycles than the other technique. So I'm not going to spend too much time on that, but I am going to ask you to implement one in a homework assignment, which you're going to have to just go find an implementation on your own. So this summary on page 141 is actually pretty good. It compares the three methods and which ones should you be using. All right, I'm actually ready to move on to linear equations on page 142. So linear equation is basically, you guys know what we're talking about. Y is equal to mx plus b. Now, come on now. Even if you've never been in any math class in the last 20 years, you probably remember y is equal to mx plus b, right? It's a way to show the graph of a line. It has a position on the x-axis by translating it this way. It has a slope for the m. So it has some sort of a slope, and then the line moves left and right until it lines up with b. So y is equal to mx plus b. Okay. So linear equations in this particular case mean something slightly different. What this means is I've got some linear equations, but I don't know. I've got an equation, I know what the answer is, but I don't know what the value of x is. So this is one of those scenarios. Let's say that some value of x, and then some value of x2, and then some value of x3, and some value of x4. So in other words, there's 4 values here I'm hunting for. I want to solve this equation for whatever x1 is, because it's being used 4 times. Whatever x2 is, it's being used for 4 times. And so I actually know the answer. The answer on the first one is 70. So no one's asking you to solve for the answer, because I already told you what the answer is. What we're trying to say is, what is the value of x1? And then what is the value of x2? And what is the value of x3? Now, if you were to do this by hand, you would take all these things together and try to do a substitution for x, okay? In this case, it wouldn't be too difficult. Well, it might be a little difficult. X would be 70 minus 7x2 minus 1x3 minus 5x4 divided by 2. Did you see what I just did? In other words, remember how this thing works? I put a minus 7x2, add minus 7x2 to this side of the equation and that side. Well, that strikes this guy out. Boop, he's gone. And then I do a minus 1x on this side and that side. Boop, he's gone. And then I end up with 2x, and I want to divide by 2. So x1 is equal to 70 divided by 2. Okay? That's how you would do the first substitution. And then you would do that over again until you got all of the things substituted. Okay, so we're after solving for these things. Now, to be complete, the linear equation has to have the same number of examples, rows in this case, same number of examples as terms. If I was hunting for 5 terms, I'd have to have 5 rows of data. If I was hunting for 18 terms, I'd have to have 18 terms of data. Now, in numerical equation world, you could have more than that, but we're not going to do that. We're always going to have exactly the same number of rows as terms, okay? That just kind of makes it easy. So, for this thing to make out, we're going to build us an array, and so this is 4 terms plus the answer, so we're going to end up with a 4 by 5 array. But we'll continue this in just a minute.